So now we're going to look at ax equals lambda x, where the idea is that we're trying to find values lambda for which there is a non-zero vector x such that a times x is equal to lambda x. Now let's think about that for a second. What it really means is we're looking for a direction x, a vector is a direction, such that if you hit that vector with a, then the net result is the same as if you simply scaled that vector. Scaling meaning you either increase its magnitude, decrease it either in the same direction or in its opposite direction, right? Alright, now this can be rewritten as lambda I minus the matrix A, quantity times x is equal to 0. And in a lot of courses you see this written as A minus lambda I versus lambda I minus A. Obviously, since there's a 0 on this side, we can always multiply both sides by -1 to flip that around, right? And the reason why we like to write it as lambda I minus A has to do with the fact that then the characteristic polynomial, which we're going to talk about later, automatically has a first term that's lambda to the m if A is an m by m matrix. Alright, now this right here allows us to say a few things, okay? And let's recall, if we have an m by m matrix that is non-singular, then that statement is equivalent to saying that B has an inverse, and it's equivalent to saying that B has linearly independent columns, that B has a null space that only contains the 0 vector, its dimension of the null space is equal to 0, and the determinant of B is not equal to 0, and as a matter of fact there was a whole list of these kinds of equivalent statements. And it turns out that as we talk about eigenvalue problems, eigenvalues and eigenvectors, what we'll do is we'll strategically pick the equivalent statement that is most appropriate for the situation. Okay, now let's think about this. This problem right here, we reformulated as lambda I minus A times x, where x is a non-zero vector, because we're looking for a non-zero vector where this is true. Now, when we look at this particular matrix, what we notice is that it has a vector x that is in its null space. What that means is that it is not the case that the null space of this matrix only has the 0 vector in it, and all of a sudden none of these statements are true. Okay? And we probably should start right here. Inherently there exists a vector x such that it is in the null space, and it's not 0. And what that then automatically means is that the matrix is singular. It does not have an inverse. It has linearly dependent columns. The dimension of the null space is greater than 0, and the determinant of this matrix right here is 0. Okay. And that's going to allow us to sort of start characterizing what eigenvectors and eigenvalues there are, and then eventually that allows us to get to where we can come up with robust practical algorithms for computing the eigenvalues and eigenvectors, which then allows us to get back to how to practically diagonalize a matrix.